Now, in the previous videos, we have started the, we can say that about the gravitation, and we have finished the Earth gravitational force. Now, the next point is the Earth's gravitational acceleration. Now, see, on the, we can say that any object when falls, that time the gravitational force acts on it, and because of that, you see the velocity of that object which is falling down goes on increases. So what happened here? We can say the body is accelerated. It is called acceleration. So it happens because of the gravitational force of Earth. So it is called as a acceleration due to gravity. See again, acceleration due to gravity means what? When any object accelerated changes its velocity by the, we can say that the application of the gravitational force of the Earth, then that acceleration is called as a acceleration due to gravity, and it is denoted by small g. Now don't confuse about the small g and capital G. This capital G, it is, we can say that it is universal gravitational constant. It is constant, it is a universal gravitational constant, and this g is there, it is a acceleration due to gravity. Now the gravitational force is there, it is directed towards the center, it is directed toward the center. At the same time, we can say that the acceleration due to gravity also directed towards the center. So we can say that acceleration due to gravity is the vector quantity, as we are denoting the, we can say, direction and magnitude. Then we can say that this acceleration due to gravity is vector quantity. Let us see how to find this value of g, small g. Then the next point is there, the value of g. Suppose one object is there and its mass is m. One object is there, its mass is m, and it, we can say that it is on the Earth surface one. So we can say that the m, capital M is the mass of the Earth, and that is the capital R is the radius of Earth. Means we can say that the one object is there, it is lying on the surface of the, we can say that this Earth one, and its mass is small m. And here we can say that the mass of the Earth is capital M, and that of the, we can say that the radius is there, it is capital R, like the radius of the Earth. Now, according to Newton's universal law of gravitation, what we have to say that the force of attraction is there is equals to G into product of masses capital M into small m upon, we can say that the r square. This distance is r, so we can say that the r square. F is equals to gmm upon r square. This is according to the Newton's universal law of gravitation. Now, one more law is that Newton's law of motion. The second law of motion is that the F is equals to mass into gravity. This is the Newton's second law of motion. This is the Newton's, we can say that the universal law of gravitation. On comparing these two, we can say that this mg equals to gmm upon r square. So we both the same, small m is there, we get cancel. So we get here this small g equals to capital G into capital M upon r square. Now if you put the value of capital G, which is 6.67 into 10 raised to minus 11, that of mass of Earth is, it is 6.4 into 10 raised to 24, and that of, we can say that the radius is 6.4 into 10 raised to 6 meter. It is square is there, so we make it here square. Means we will put the value of capital G 6.67 into 10 raised to minus 11. Capital M, that is the mass of Earth, 6.4 into 10 raised to 24. And that of radius of the Earth is 6.4 into 10 raised to 6 bracket square. On simplifying this, we'll get the answer 9.77 meter per second square. That is the, we can say that the value of small g. The value of small g is 9.77 meter per second square. This is the, we can say that the when object is on the surface of the earth. It means that if you see the formula of the small g, it is gmm upon r square. What it says that? It says that the value of g does not depend on the mass of the any object. It means you can take whether paper or you can take suppose any a big boulder which has suppose 100 kg mass. Okay, so you can take any one big stone you can take, or you can take any paper. On all the objects one, the gravity, the acceleration due to gravity, that is the gravitational, the acceleration due to gravity is 9.77 meter per second square. So we found that now value of g is 9.77 meter per second square. But this value of g varies if we go on the surface of Earth. Means even though we got the value g equal to 9.77 meter per second square, that value varies. So let us see the variation in the value of g. First, changes along the surface of Earth. Now see the shape of Earth. The shape of Earth is, we can say that the not perfectly spherical. It is not, we can say that the perfectly spherical one. So what happened here, as the, we can say that the shape is not perfectly spherical one, that time here we can say that we can see that the at the equator the earth is bulges out, and here at the pole it is a, we can say, north pole and south pole. At the pole it is, we can say, flattened. That is the, we can say, shape of the earth. Now what happened here, if we see the radius one, this radius is from the, we can say, center to the poles. This radius are smaller than the, we can say that the from the equator one. If you find the radius from the ends of the equator and the radius from the poles one, this radius of the poles are smaller than. It means here this distance is less. It is near to the center of the earth. So what happened here, the gravitational force is more. As gravitational force is more, what happened here, the value of g is found to be 9.83 meter per second square. It means here, as the shape of the earth is not perfectly spherical one, it is called, we can say, oval shape. The at every point the radius changes one, and here we can say that the at the poles one, this radius is smaller than the radius at the equator one. So what happened here, the value of g at the poles is 9.83 meter per second square, while the value of g at the equator is 9.77 meter per second square. So here, because of the, we can say that the not perfectly spherical shape, we get the value of acceleration due to gravity, value of g is different. It is because we can say that there is a variation in the gravitational force one. If this part is near to center of earth, so we can say that the value of g is greater, and this part is, we can say that the little longer one, more distance is there, so we get the, here we can say that the value of g at the equator is 9.77 meter per second square. So because of different shape, not spherical shape, we get a different value of g. It means the value of g varies. Now second factor of it, that is the changes in height. Now see, if suppose object is at the surface one, the value of g is, we can say, 9.8 meter per second square. It's practically now here 9.77, here 9.83. So practically we are taking the value of G, it is 9.8 meter per second square. This is the practical value we are taking. Now it means at the surface of the earth value of G is 9.8, we can say meter per second square. Even suppose there is a one aeroplane is there, okay, it is, we can say that a 10 kilometer one. 10 kilometer, here suppose we can say that the one aeroplane is there, which is, we can say, moving one. Now even though it is a 10 kilometer one, we know the radius of the earth is 6400 kilometer. The height will be, we can say that the 6410 kilometer. This height will be now 6410 kilometer. Then too the value of G remains same, near about 9.8, we can say, meter per second square. Now if we go above that, means above you go like this, above, like this, we can say that 36.6 kilometer, means we can say that the man-made balloon which was reached at the height of, we can say, 36.6 kilometer. Now see, the atmosphere is 40 kilometer from the surface of earth, 40 kilometer atmosphere is there. So man-made balloon reached up to 36.6 kilometer one. So at that point the value of G is found to be 9.77 meter per second square. At where? At the, we can say that the 36.6 kilometer one. If you go beyond that one, means suppose we can say 400 kilometer one, where the, we can say that the satellites are, we can say, space satellites we are sending. So at this place 400 kilometer one, the value of G decreases 8.7 meter per second square. Again more further it is, if we go, if we suppose the communication satellites are same 35,700 kilometers, means from here, if suppose the, it is 35,700 kilometers from the surface of earth to till, we can say that the 35,700 kilometers, the value of G again decreases, it becomes 0.225, we can say, meter per second square. It means that if we go out away from the center of earth, if we go away from the center of earth, the value of G decreases. It means as the height of the object increases, height of the object increases, it means its distance from the center of earth increases one, that time the gravitational force act on it also decreases one, and then what happens, then the value of G also decreases one. So from this table we can say that the, as the object move away from the center of earth, is as the height increases, then the value of small g decreases. Now the third factor which affect the value of G, that is the changes in depth. Now you see here, if suppose what we are saying now, the object is going away from the center of earth, that time what happens, the value of G decreases one. It means if suppose the object is coming on the surface, the value is coming is a 9.8 meter per second square. If suppose if you bring that object near to the, we can say, center of earth, what happen here, on the, at the surface, at the center of the earth, what happen here, the value of G becomes 0. Why 0? Because here now there is a no gravitational force. Okay, so here value of G is, we can say that it becomes 0. Now what happens, again we have taken the object now below, that's why we said here changes to the depth. If suppose the object is taken down to the depth one, what happen here, again the value of G is there. Here the value of G again we can say that it decreases one. Means what happen here, when the object is taken down here, what happen here, the height we can say that, no, not height, the depth we can say that to the depth one, here this distance we can say that the G, the value of G decreases, as well as the, we can say that the mass also decreases. The mass of earth also here decreases because of decreasing value of G, and the value of the, we can say, mass of the earth is the less one, by combining the effect what happens here, the value of small g also decreases one. So one thing you have to remember now, the if first point what you have seen that the changes along the surface of Earth. The shape of the Earth is not perfectly spherical one, it is oval shaped one, it is bulges at the equator and flattened at the pole. This distance is less, so we can say that the value of G at the pole is 9.83, while at the we can say equator is 9.77. But what I said here now, when you go away from the we can say center of Earth, as the height increases one, the value of G decreases. As the gravitational force decreases one, value of G also decreases one. In the same case, changes with the depth one. If the suppose object is coming down, okay, below the center of Earth, then what happen? The value of gravitational force decreases, no doubt. The here what happen? Mass of Earth also decreases one because of combining the effect of this. So we can say that the gravitational force, decreasing gravitational force and decreasing mass of the Earth, we can get the value of small g also decreases one. This is about the we can say these three factors one. Now, after studying these three factors, the next point is that is the mass and weight. Actually, see, always we say that the 10 kg weight, 20 kg weight, the weight and mass both are the different quantities. Mass is there, mass is the we can say that the scalar quantity. While weight is there, it is a vector quantity. Mass means we can say that the quantity of matter contained in an object. Mass means the quantity of matter in an object. While weight means the force which the gravitational force which acts on the we can say object. So weight is nothing but the force. Weight is nothing but the force which acts on the object. Means here which force is there? Gravitational force. So weight is nothing but the gravitational force which acts on the we can say that the object one, that is called weight. And when we say about the mass one, mass is the scalar quantity one, and here the mass is the quantity of matter contained in it. When we say that the 10 kg, so 10 kg is the mass, not the weight one. So when we are saying somebody's weight is 40 kg, so here what we are going to say that here the mass is 40 kg, weight is not there. If we say weight, and what happens here, if you want to find the weight of that particular person one, suppose 40 kg, suppose we are saying the mass is there, if you want to find weight, you have to multiply this 40 by 9.8. Because we know that this force is nothing but force is equals to mass into gravity, that is the Newton's second law of motion. So F is equals to m into g. So mass is 40, so 40 multiply g. After multiplying, whatever answer you get, you will get in the Newton. It will come 4 8s are 32, 3 carry 4 9s are 45 plus 3 48, 482 Newton. So we can say that the person having mass 40 kg, its weight is 482 Newton. So the weight and we can say that the mass are the different quantities. Now the next point is the free fall. Suppose I hold this duster. Now what happened here? On this duster, a gravitational force acts. At the same time, there is a we can say that the one upthrust is there, one buoyant force is there, acting from the under the we can say palm. Because of gravitational force and this upthrust one, or we can say that the another force is there, okay, downward force is there, which is pointing upward one. So this both these forces, buoyant force and gravitational force, both are equal. That's how what happened. This duster is the rest one. Now suppose if I remove my we can say palm, if I leave it, it will fall down. It means we can say that now only it moves, the duster moves downward direction under the influence of gravitational force. So when any object moves vertically downwards under the influence of gravitational force alone, then that falling of the object is the free fall. Means any object when falls vertically downwards only because of the, we can say that the under the influence of gravity alone, under the influence of gravity alone, then we can say that the it is free fall. So for free fall, see, initially the object is at the, we can say that the rest one. So initially means we are taking value of small u. For denotation we are using the small u as a initial velocity. It is taken as 0. And then we leave it, it falls down. Its velocity goes on, increases 1. Okay. So what happened here? When any object, we can say that the falling down under the influence of gravity, then we can say that the it is a free fall. Now see, in the ninth standard you had only three equations one, that kinematical linear equations one, that is u is equals to v plus at. That was the first, we can say that the equation was there. Second equation, another equation, s is equals to ut plus half at square. And third was that is the v square is equals to u square plus 2as. These were the three kinematical equations last year we learned in the ninth standard. Now suppose the object is falling, we can say under influence of gravitational force, is during the free fall, the value of, we can say u equal to 0 and acceleration equal to z, means you can take u equal to 0 and a equals to g. So what we get here, 0 equals to v plus, we can say that the the equation of v is equal to u plus at. It is v is equals to u plus at. So if you put the value of, we can say u equal to 0, we get v is equals to 0 plus gt. So we get here v is equals to gt. Then second is that if you put again here u equal to 0, s is equals to, what we get here, half gt square. And again here, if you put the values, what we get here, the v square is equals to 2gs. Means by using these three equations, you can find the velocity of the object at particular time. When the value of g is taken 9.8, you can find the, we can say that the height of the object from the, we can say, surface of earth. By again putting the, after certain time you can find this value of s also. It is the height of the object from the surface of earth. Then you can find from this, you can say the velocity of the object one. These three are there that can be used to find the velocity motion of the object at different times. Also the, we can say, displacement of the object from the surface of earth at different times. So these three equations are used one. In the ninth standard, you learn about the potential energy. Okay, so mechanical energy of two types, kinetic energy and potential energy. So potential energy is nothing but the, we can say, energy because of the, we can say, a state or position or configuration of the substance. We suppose a water is stored in the dam, it is at the larger height one. So because of that, what happened? The water gets the potential energy. So potential energy that we measure, that is with the help of formula, mass into gravity into height, mgh. This is the formula to find the potential energy of the object one. Now again you see, imagine like this here, there is the, we can say that the earth, which is not in the, we can say that perfectly spherical one. Now here at the surface of earth, from here, suppose at the certain height, if you go away from the, we can say that this surface of the earth, near about the, we can say that 35,700, this communication satellite we say, suppose. What happened here? The value of g decreases. Again we will go beyond that one. What happened here? The value of g becomes 0. If the value of g becomes 0 here, g equal to 0, it means that mass into 0 into height. This height is infinite one. We are not knowing height now, how many height is there. It may be more than 35,700. So here mass into, that is gravity, which is 0 1 into h, we will get the potential energy 0 here. It means here the potential energy is 0. Now suppose if you bring that object near to the surface of Earth, suppose at this height, suppose this height is h, your object is there. So the total height is, we can say that be r plus h. So here what happened, as the value of g is 0, if you bring the object near 1, okay, the value of g again decreases. Now the value of, we can say, the potential energy decreases here. Here it is 0. Now if you bring the object near to the surface of the earth one, what happen here? It will below the 0. Below 0 means it will become negative. So we can find the potential energy of that object by formula, potential energy equals to minus G capital M into small m upon R plus H. By this formula we can find the potential energy. Why it is taken negative? See, below, above the, we can say that the certain height one, infinite height one, value of G is 0. Again you bring the object nearer, the value of, we can say that the g will increase, no doubt it will be more, but the, we can say that the potential energy will be decreased one. So it is decreased means it becomes negative one. So potential energy is written as minus gmm upon r plus h. That is the, we can say, formula to find the potential energy of the object which is kept at the height h from the surface of earth. This is about the gravitational potential energy. Now last one is there about the escape velocity. Now escape velocity. Now suppose see, if we throw any object vertically upward, what happen? It will attain certain distance. Suppose this duster is there. If I throw vertically upward, it will attain. It will, its velocity goes on, decreases one. At certain height, it will stop. Again, coming down. It means after throwing vertically upward, what happens? Its velocity goes on, decreases one, and it attains certain height, and again that object comes down. If I increase the initial velocity more, if I give the more initial velocity one, what happens? It will attain more height one, and then once velocity becomes 0, again it will coming down. Now what I will do? I will give the initial velocity equal to the, we can say, escape velocity. Means I will give the velocity to that, we can say that the object one, so that it will go away from the, we can say, gravitational force one, and that object will not come back. So the velocity with which the object is going away from the gravitational force, it, we can say that the leaves this, we can say that the gravitational force, and it doesn't come back, then that velocity is there. It is called as a escape velocity. Escape velocity is a velocity given to the object so that object goes beyond the, we can say that the surface of the earth one, and from there it doesn't come back one. So the whatever velocity is given initially to move the object vertically upward, and so that it will not come back, then that velocity is there. It is called as a escape velocity. So students, we have finished this chapter 1. So we'll go through it, read the chapter carefully, okay, watch the video, all the 3 videos I have given to you, watch these 3 videos again and again, so that whatever difficulties are there, that will be clear one. I know that is, see, each and every topic I have taken thoroughly. I think so you won't get difficulty, but still I will say that you read the lesson carefully, whatever the activity based questions are there, that you try to find the answer one. If they ask with the internet, use the internet, find the answer one, so that you will gain the more knowledge. So it is better not only depend on the, we can say that, we can say, only watching the videos one or reading the textbook one, you find the answer also. One more thing is there, whatever examples are given in this textbook one, which are solved one, try to solve it, and even unsolved example also. After the, when school will start, that time we'll see this example one. But my opinion is that first you try to solve yourself one, so that if you are difficulty one, we can try in the class one.